Metal is the primary structural material of the modern environment, appearing in everything from the fragile foil in a kitchen to the massive steel cables of a bridge. Aluminum foil and steel I-beams seem to have nothing in common, yet they share the same classification. If such different objects are both called metals, there must be a common logic that links them. This logic is found in their physical properties, a set of predictable traits that define what a metal actually is and how it will react to the world. Identifying these traits allows engineers to move beyond simple appearances and accurately predict how a material will perform, whether it is supporting a skyscraper or carrying an electrical charge. The easiest way to group elements is by checking their physical traits. Take this piece of metal. It might look dull or tarnished, but if the surface is scraped away, it reveals a reflective finish underneath. Chemists call this predictable shine metallic luster. Then there is hardness. If you strike iron or zinc with a hammer, they hold shape. This rigid, unyielding structure is why we rely on metals for heavy construction and durable tools. But there are immediate exceptions. Take sodium. It is a metal, yet ignores the hardness rule. If you take a kitchen knife to a piece of pure sodium, you can slice right through it like a stick of room temperature butter. Shine and hardness are excellent baseline indicators, but exceptions like sodium prove that visual appearance and texture alone cannot provide a complete definition. To find universal traits, we must look at how materials respond to extreme physical stress. When you hit a piece of coal with a hammer, it shatters. When you hit a metal, it absorbs that kinetic energy and flattens into thin sheets. This property is known as malleability. Silver and gold represent the peaks of malleability. They can be beaten down to microscopic thicknesses without breaking or cracking. Metals also possess ductility, the ability to be drawn out into thin wires. Take a single gram of pure gold. Thanks to extreme ductility, you could stretch that single gram into a continuous wire spanning 2 kilometers before it finally snaps. This combination of malleability and ductility allows humans to take raw elements from the earth and form them into specialized tools for every level of industry. We use metals like copper and aluminum for cooking pots because they have high melting points and act as excellent conductors of heat, distributing thermal energy quickly and evenly. They are equally effective at conducting electricity. The utility workers navigating these power lines rely on the fact that the metal wires carry the current, while a non-conductive coating, like PVC, acts as an insulator to prevent the energy from escaping. Even sound behaves uniquely here. When metals are struck, they produce a sustained, ringing tone. This property is called sonority, and it is the reason school bells and musical instruments are cast from metal alloys. Metals act as high-speed conduits. Because they transfer thermal, electrical, and kinetic energy so effectively, they serve as the essential hardware for power grids and communication lines. Up to this point, we have a reliable physical checklist. To identify a metal, we look for an element that is hard, shiny, malleable, ductile, conductive, and sonorous. But the deeper you look into the periodic table, the more the checklist fails. Consider mercury. It is perfectly reflective and conducts electricity, but it exists as a liquid at room temperature. Take elements like gallium and cesium. They technically exist as solids in a cool room, but their melting points are so low that they will turn into a liquid puddle from your body heat alone. These contradictions create a scientific dilemma. If our primary metrics are riddled with exceptions, we cannot rely on physical traits alone to categorize the universe. To establish unbreakable rules, scientists had to look past what they could see and touch. They had to investigate the atomic level and observe how these elements chemically react, setting the stage for a deeper classification. Look around your kitchen or your garage, and you are mostly looking at metals. We use them to build the modern physical world because they are inherently strong and durable. But over on the right-hand side of the periodic table sits a tiny minority group, the nonmetals. They lack that heavy-duty strength, but they make up the foundation of our atmosphere and organic life itself. There are very few of them compared to the metals. At room temperature, you will almost always find them existing strictly as either a solid or a gas. There is exactly one exception to that rule. Bromine is the sole nonmetal that exists as a liquid. To figure out how to accurately organize these elements, scientists run them through a series of physical tests, measuring their traits directly against the heavy-duty baseline of metals. The first test is about physical shape. Metals are famous for being malleable and ductile. That means you can hammer them into flat sheets or pull them into long, thin wires without them breaking. Try that with a solid nonmetal, and you get a completely different result. If you strike a chunk of sulfur with a hammer, it doesn't bend, it shatters into pieces, because solid nonmetals are highly brittle. Next is the eye test. In their pure state, metals possess a highly reflective surface. Chemists call this metallic luster. Nonmetals generally absorb light. To the naked eye, they look flat and dull. Finally, we test for conductivity. Metals easily allow both heat and electricity to flow right through them. Nonmetals block that flow, acting as insulators. Based on these sensory tests, the periodic table seems perfectly sorted. Nonmetals behave as the exact physical opposites of metals. But that neat organization falls apart the moment you look closely, starting with a nonmetal that shines like a polished mirror. Iodine is classified as a nonmetal, yet it completely ignores the rule about being dull. It possesses a bright metallic luster. Then there is the issue of conductivity. One specific form of carbon outright ignores the rule that nonmetals must act as insulators. Graphite is an allotrope, meaning a different physical form, of carbon. If you wire it into an electrical circuit, it conducts electricity perfectly well. Carbon strikes again with another allotrope, diamond. It proves metals don't hold the monopoly on strength by being the hardest natural substance known on Earth. The metal category has its own problems. The alkali metals, like lithium, sodium, and potassium, are so incredibly soft that you can slice right through them with a standard kitchen knife. And mercury refuses to be a solid at room temperature at all, pooling into a dense, shiny liquid. Because nature relies on these strange paradoxes, chemists realize that attempting to classify elements purely by looking at them and hitting them with hammers is an unreliable system. To properly categorize an element, scientists have to look past its physical surface. The true metric lies in how it behaves chemically, specifically what happens when you burn it in oxygen. When you burn a metal like magnesium in the air, it reacts with oxygen to leave behind an ash. When you take that ash, the metal oxide, and dissolve it in water, it creates a new solution. This diagram illustrates that core chemical reaction. Metal plus oxygen yields a metal oxide. If we dip red litmus paper into that dissolved oxide solution, it turns blue. That color change proves the metallic solution is basic. Now look at what happens when we swap in a nonmetal, like sulfur. A nonmetal plus oxygen yields a nonmetal oxide. We dissolve those fumes in water, test it, and this time blue litmus paper turns red. That proves the nonmetal solution is acidic. That chemical footprint, producing a basic oxide versus an acidic oxide, is the true dividing line of the periodic table. It gives us a reliable way to sort elements, regardless of what physical disguise they are wearing. Physical traits can trick you, and those tricks show up constantly on chemistry exams. Let's run through the 3 major non-metal rule breakers you need to remember. Exception 1 is iodine. It is a non-metal that steals the metallic trait of having a shiny luster. Exception 2 is graphite. This form of carbon ignores the insulation rule and freely conducts electricity. Exception 3 is diamond. Also a carbon form, it beats the metals at their own game by being the hardest natural substance. In chemistry, an element's true identity is never defined just by how it looks on the surface. It is defined by how it chemically reacts when pushed to its limits. We build our world with metals because they seem unchanging. Skyscrapers, bridges, and bank vaults are designed to stay structural for lifetimes. But chemically, that stability depends entirely on which element you're holding. On one side of this screen, a metal is bursting into flames the moment it touches the air. On the other, a gold artifact rests at the bottom of the ocean, unblemished after thousands of years of submersion. This gap in behavior is the central problem of metallurgy. We need a way to measure and rank these different chemical personalities. We can do that by running a series of escalating stress tests, using the Earth's 2 most abundant resources, oxygen and water. By subjecting these elements to identical, controlled trials, we force them to reveal their position in a natural hierarchy of reactivity. Phase 1 is the air test. When metals are exposed to oxygen, they undergo a fundamental change. As shown in this equation, the metal and oxygen combine to form a new compound, a metal oxide. Sodium and potassium fail this test immediately. At room temperature, raw sodium oxidizes so rapidly it smokes and bursts into a bright flame in seconds. Because of this immediate reaction with air, these metals are stored submerged in kerosene to block any contact with oxygen. Magnesium sits one step lower. It stays stable on a lab table, but once you apply heat, it burns with a dazzling white flame. Copper is more stubborn. It refuses to burn at all. When heated, it simply coats itself in a dull black layer of copper-2 oxide. These oxides also reveal a distinction in chemical character. While most metal oxides are basic, aluminum and zinc produce oxides that can react with both acids and bases. This dual behavior is known as being amphoteric. Finally, we have silver and gold. Even at extreme temperatures, these metals refuse to react with oxygen, earning them their status as noble metals. The oxygen test separates the most volatile elements from the inert ones, but we need a harsher environment to sort the metals in the middle of the list. That leads to phase 2, the water test. By using water as a multi-stage filter, we can increase the energy of the test to see exactly when each metal breaks. The chemistry follows a tiered rule. As seen here, reactive metals strip oxygen from water to form an oxide or hydroxide, releasing flammable hydrogen gas. In cold water, sodium and potassium react instantly. The heat ignites the hydrogen gas, sending the metals skittering across the surface in a localized fire. Calcium is less violent. It reacts with cold water without catching fire, though it produces enough hydrogen bubbles to lift the metal to the surface where it floats. Magnesium ignores cold water entirely. It requires the higher energy of hot water to begin reacting and floating on its own gas bubbles. Then there are the metals that only react with steam. Aluminum, iron, and zinc ignore liquid water at any temperature, only breaking down when exposed to high-energy water vapor. At the very bottom, lead, copper, silver, and gold remain unaffected by water in any state. Water functions as a tiered chemical filter. By stepping up the energy from cold liquid to steam, we fracture the elements into distinct tiers based on the thermal energy required to force a reaction. These test results follow a specific pattern called the Reactivity Series. Combining our observations, we build a hierarchy ranking elements from highest reactivity to lowest. This list maps directly to our tests. Top elements failed the cold water trial. The middle tier required steam. The bottom group survived both tests completely. This explains why sodium storage is a common focus in chemistry. Its position at the top of the series means it reacts with both air and water almost instantly, requiring isolation in kerosene to remain stable. We have mapped this hierarchy using the natural elements of air and water. In the next stage, we'll see what happens when we move beyond nature and subject these metals to the concentrated power of industrial assets. If we drop different metal samples, like magnesium, aluminum, zinc, iron, and lead, into identical test tubes of dilute acid, we can immediately see that they don't all behave the same way. The baseline chemical rule here is straightforward. When these metals react with a dilute acid, they produce a salt and release hydrogen gas. But look closely at the tubes. By observing the speed of the bubbles forming and measuring the heat generated, we can rank them. Magnesium bubbles violently and gets the hottest, while iron produces bubbles very slowly. The chemical formula is identical for all of them, yet the extreme differences in speed and heat prove that these elements exist in a strict hierarchy. There is a major exception to this rule: nitric acid. When we drop a metal in here, we don't get the standard hydrogen gas release. To see why, we have to look closer at the molecules. Nitric acid acts as a strong oxidizing agent. As the reaction attempts to produce hydrogen gas, the nitric acid intercepts it. It oxidizes the hydrogen, converting what would have been gas into drops of liquid water. We can push this oxidizing behavior further by mixing 1 part nitric acid with 3 parts hydrochloric acid to create aqua regia. This highly corrosive mixture forces completely unreactive metals, even solid gold, to dissolve. Chemical rules have boundaries. Understanding the mechanics of an oxidizer helps resolve these exceptions. Let's test this hierarchy directly by forcing 2 metals to compete. In this split screen, we have an iron nail sitting in a copper sulfate solution on the left and a copper wire inside an iron sulfate solution on the right. We are testing for a displacement reaction. The logic is that a more reactive metal will steal the position of a less reactive metal within a compound. On the left, the iron nail pushes the copper out of the solution. The liquid fades from blue to green, and a brown layer of displaced copper builds up on the nail. Over in tube 2, the copper wire sits in the iron solution, and nothing happens. The copper is too weak to displace the iron. Because this reaction only works in one direction, it provides the clear evidence required to rank one metal above the other. By combining our observations from the acid bubbling tests and these displacement competitions, we can rank the elements on a vertical leaderboard. This definitive ranking is known as the Reactivity Series. Notice that hydrogen is included here, even though it's a non-metal gas. It acts as the dividing line. The metals placed above it react with dilute acids, while the metals below it do not. Let's put this tool to work. If we mix solid zinc with iron sulfate, what will the result be? Pause the video, find zinc and iron on the Reactivity Series, apply displacement logic, and find the answer. Let's check the board. Zinc sits higher than iron on the list, meaning it is more reactive. Because of this, zinc will displace the iron, resulting in zinc sulfate and solid iron. This summarizes the three main rules. Standard metals and acids yield salt and hydrogen gas. Nitric acid produces water instead. In a head-to-head match, the higher metal displaces the lower. Memorizing the exact order of this series is much easier with a mnemonic. Please send cats, monkeys, and zebras in lovely, happy cages made of silver and gold. The first letters map directly to the elements: potassium, sodium, calcium, magnesium, aluminum, zinc, iron, lead, hydrogen, copper, mercury, silver, and gold. Internalizing this hierarchy turns these separate reactions into a predictable system, providing the foundation needed to understand ionic compounds in our next lesson. If you look at elements in their pure states, most are restless. They react, sometimes violently, because they are seeking a specific target, the perfect, stable electron balance of a noble gas. This table displays the electronic configurations of noble gases, metals, and nonmetals. The outermost shell, the valence electrons, dictates how every atom reacts. Noble gases already have a full outer shell, making them stable. Everyone else has to work for it. To get that full shell, elements take one of two paths. Metals shed their outer electrons to expose the full shell underneath. Nonmetals do the exact opposite. They pull in outside electrons to fill the empty slots in their current shell. When a metal and a nonmetal meet, it is a perfectly matched transaction. The metal gets rid of the exact electrons the nonmetal needs to steal. Both parties walk away with a full outer shell. Let's look at a one-to-one exchange between sodium and chlorine. Sodium has one extra valence electron. Chlorine has one empty slot. Sodium hands its electron over to chlorine. Notice what happens to the math here. Sodium still has its original 11 positive protons in the nucleus, but now it only holds 10 negative electrons. Losing a negative electron leaves it with a net charge of +1. It is now a positive ion, or a cation. Over on the chlorine side, the math flips. It keeps its 17 positive protons, but now holds 18 negative electrons. Gaining that extra electron gives it a net charge of -1, making it a negative ion, or an anion. Because positive and negative charges attract, strong electrostatic forces pull these two ions tightly together. But they do not stop at a single pair. These forces radiate in all directions, pulling in millions of oppositely charged sodium and chloride ions. They stack into a massive repeating three-dimensional lattice. This entire three-dimensional lattice is held in place by an invisible network of electrostatic attraction. That collective pull is the ionic bond. The math isn't always a clean one-to-one swap. Take magnesium. It has 2 valence electrons to give away, but if it approaches a chlorine atom, chlorine still only has 1 empty slot. Magnesium tries to unload both electrons to reach stability. Chlorine takes the first one, but rejects the second. Its shell is completely full. Magnesium is stuck holding an extra electron, leaving it unstable. How does it complete the transfer? It recruits another atom. A second chlorine atom steps in to accept the final electron. Now we have 1 magnesium ion with a +2 charge and 2 chloride ions, each with a -1 charge. This required ratio is exactly what a chemical formula represents. MgCl2 tells us that to balance the electron transfer perfectly, you need 1 magnesium atom for every 2 chlorine atoms. That microscopic lattice structure directly controls how the compound behaves in the real world. For example, ionic solids are brittle. If you hit the crystal, the layers shift. Positive ions suddenly align with other positive ions. They violently repel each other, and the crystal shatters. Those electrostatic bonds are also incredibly strong. To melt an ionic solid, you have to apply massive amounts of heat energy to finally break the rigid ions apart. And then there is electricity. In a solid state, the ions are locked tightly in the lattice. They can't move, which means they cannot conduct an electrical current. But if you dissolve the compound in water or melt it down, the ions break free from the rigid structure. Now that they can float and move, they can successfully carry an electrical charge. Every physical property you can see or test, how it breaks, how it melts, how it conducts, is strictly dictated by the strength and mobility of those microscopic ions. When you solve these problems on an exam, stick to the golden rules. Draw out the exact electron transfer, track the net charges to write your formula, and remember the conductivity catch. Ionic compounds only conduct electricity when molten or dissolved. Behind all the math and the formulas, it boils down to one simple drive: elements trading whatever they have to just to achieve the stability of a noble gas.
We are used to metals being sleek and shiny, the pristine skeletons of our cities. But out in the wild, they look nothing like that. Nature rarely hands us a pure, gleaming chunk of copper or iron. Instead, it buries them deep underground, trapped inside heavy, dull rocks known as ores. If you look at this model of a typical metal atom, you can see why. Metals carry a few extra electrons in their outermost shell, making them unstable. To reach a balanced, comfortable state, they try to shed those outer electrons. And there are plenty of elements in the earth, like oxygen and sulfur, that are more than happy to snatch up those discarded electrons. When they do, the opposite electrical charges lock the metal and the oxygen together into an incredibly strong ionic bond. So the very trait that makes metals so useful to human civilization, their loose, free-flowing electrons, is the exact reason they are almost always found bonded to dirt. We can rank how desperately an element wants to shed its electrons. Chemists call this the Reactivity Series, a strict hierarchy that tells us exactly how fiercely a metal is trapped inside its ore. Down at the very bottom, you have low reactivity metals like gold and silver. They hold on to their electrons tightly enough that you can actually pan them out of a riverbed completely unbonded, as pure native metal. But look at the top of the list. Elements like sodium, potassium, and aluminum are so eager to lose electrons that they form intense bonds with their surroundings. Sodium will even catch fire if it touches the moisture in open air. To get the materials we need, we have to find ways to override that chemistry. The history of metallurgy is really just a timeline of humans finding more intense ways to provide the energy required to pull these elements apart. Breaking those natural bonds requires a massive input of external energy, creating what we can think of as a thermodynamic debt. We are using brute force to rip the metal away from its preferred, stable state. For metals situated lower on the reactivity series, you can get away with basic heat. Apply enough of it, and the chemical bonds simply shake apart, leaving the pure metal behind. But for medium reactivity metals, like iron and zinc, heat alone isn't enough. We have to introduce a chemical thief, carbon. When thrown into a blast furnace, the carbon acts as a reducing agent. It steals the oxygen away, leaving the molten iron to pool at the bottom. For the most stubborn metals, at the very top of the series, even carbon is useless. To break those ores apart, we have to blast them with massive, continuous currents of pure electricity. Regardless of the method, industrial extraction is an exercise in defiance. We force immense energy into a stable rock to strip away its natural chemical bonds. We can even weaponize the reactivity series against itself through displacement reactions. If you introduce a highly reactive metal to a compound of a less reactive one,
the stronger metal will forcefully steal the oxygen for itself.
You see this play out dramatically in the thermite reaction, which engineers use for fusing heavy railroad tracks together right in the field. They mix powdered aluminum with iron oxide. Because aluminum is far higher on the reactivity scale, it aggressively rips the oxygen away from the iron. The reaction releases so much heat that the resulting iron is left completely molten, instantly welding the steel rails. Yet, even after these violent extraction methods, the resulting metal is rarely perfect. It is often riddled with microscopic trace elements that compromise its physical strength. This diagram shows how we fix it. Through a process called electrolytic refining, we run an electric current through a chemical bath, causing the impure metal block to dissolve. Its atoms migrate across the liquid and deposit themselves onto a pristine plate, rebuilding the metal atom by atom. While sheer force gets the metal out of the ground, it is this atomic-level precision that provides the reliable foundation required to build the modern world. Holding on to that pure metal comes at a cost. Because it exists in an unstable state, carrying all that stored energy from the furnace, the metal is constantly looking for an excuse to return to its natural form. We see that cost in corrosion, or rusting. The moment iron is exposed to environmental oxygen and moisture, it begins reacting. Rusting is exactly the extraction process running in reverse. The iron is releasing the energy we pumped into it, bonding back with oxygen and slowly degrading into a stable, brittle compound. Every steel beam, truss bridge, and copper wire sits on a ticking clock, giving up its electrons in a bid to return to the ground. To stop our cities from crumbling, we have to cheat time. One method is sacrificial protection. By coating a steel pipe in a layer of zinc, a process called galvanizing, the more reactive zinc corrodes first, absorbing the damage and keeping the iron underneath safe. An even deeper intervention is alloying. By melting different elements together, like adding chromium to iron to make stainless steel, we alter the metal's internal crystal structure. This creates a barrier that physically blocks oxygen from reacting. And sometimes human engineering achieves something that seems to defy the rules altogether, like the famous Iron Pillar of Delhi. Forged over 1,500 years ago, this massive iron structure has stood fully exposed to the elements, yet it has barely rusted. Ancient metallurgists used a specific concentration of phosphorus in the iron, which triggered the formation of a dense protective film over the surface, halting the reactivity cycle. It is a striking reminder that while nature eventually tries to reclaim what we've mined, we are not helpless against it. Progress is measured by our ability to master these materials, balancing their immense utility against their constant chemical urge to return to the earth.